400 million years after the Big Bang, the universe should have been boring. According to our best models, it was a foggy, slowly brightening place where the first tiny galaxies were just learning how to shine. Then James Webb opened its golden eye and saw something that should not exist. James Webb is not just a better Hubble, it is a different kind of machine. Its 6.5-meter segmented mirror collects over 6 times more light than Hubble's, and it is tuned to infrared wavelengths, the kind of light that feels like warmth on your skin. That matters, because the early universe is racing away from us. As space expands, light from distant galaxies is stretched or redshifted from visible into infrared. Hubble could glimpse this ancient light only at the edge of its sensitivity. Webb was built to swim in it. To see how shocking Webb's discoveries are, we need a baseline expectation. In the standard LAO-CDM cosmology, that's lambda cold dark matter, structure in the universe grows hierarchically. Tiny clumps of dark matter form first, gas falls into these gravitational wells, cools, and forms the first stars. Those stars explode, stir the gas, and slowly over hundreds of millions of years, build up larger galaxies through mergers and accretion. It's a cosmic version of building a city. You start with villages, then towns, then megacities. By the time the universe is a few 100 million years old, we expect mostly villages of stars, not galactic skyscrapers. There's another important piece. The universe began in a hot plasma, then cooled enough for neutral hydrogen atoms to form. After that, for a few 100 million years, space was filled with a kind of cosmic fog of neutral hydrogen that absorbs ultraviolet light. Astronomers call the end of this foggy era reionization, when the first stars and galaxies pumped out enough energetic photons to strip electrons off hydrogen again, making the universe transparent. Before reionization, bright galaxies should be rare and small, because star formation is just getting started and the fog chokes off their light. So when Webb started its early release science programs, surveys like Shears and Jades, astronomers expected to find a modest number of faint baby galaxies at redshifts of 8, 10, maybe 12. A redshift of 10 means we see the galaxy as it was when the universe was only about 500 million years old. These would be dim smudges, barely there, each containing maybe 100 million solar masses of stars. Instead, the first deep images came back, and the data were littered with tiny, intense little red dots and surprisingly bright galaxies that seemed far too massive, far too early. Those little red dots are not literally red in space. Their light has been stretched by cosmic expansion. In Webb's infrared cameras, they appear as compact reddish points, often unresolved even with its huge mirror. Their colors, how bright they are in different filters, suggest extreme redshifts, sometimes 10, 12, even beyond 13. That pushes them into the first 300 to 400 million years after the Big Bang. But here's the twist. Many of these dots are not just red, they're bright. Brightness combined with distance implies a lot of stars, or something even more energetic. It's as if you looked at a baby picture of a city and found a fully lit skyscraper district already in place. To turn brightness into physics, astronomers build spectral energy distributions. Essentially, they fit models of stellar populations and dust to the observed colors. From this, they estimate stellar mass and star formation rate. For some Webb galaxies at redshifts around 10, the inferred stellar masses are on the order of 10 pound 9 to 10 pound 10 solar masses. That is 1 billion to 10 billion suns worth of stars, assembled when the universe is only a few % of its current age. In LED-CDM, building that much stellar mass so quickly is hard. Gas must collapse, cool, form stars, and survive feedback from supernovae and black holes, all in a cosmic blink. The models can be stretched, but some of these objects sit right at, or beyond, the edge of what we thought was possible. And then there are the red and blue monster galaxies. Some early Webb discoveries show a puzzling combination. Very red overall colors, suggesting old or dust-obscured stars, but with pockets of intense blue light, indicating hot, young stars forming like crazy. Red can mean two different things in astronomy. It can mean old, because older stars are cooler and redder. Or it can mean dusty, because dust grains preferentially scatter blue light. and let red and infrared through. When you see a galaxy that is both massive and red at high redshift, you're either looking at a surprisingly mature system or at a galaxy already choked with dust from previous generations of stars. Both scenarios imply a lot of prior star formation in very little time. To disentangle this, Webb doesn't just take pictures, it takes spectra. By spreading the light out into its component wavelengths, astronomers can look for specific fingerprints, emission lines from ionized oxygen, hydrogen, and other elements, and absorption features from old stars. These lines tell us redshift precisely, and they reveal the chemical enrichment of the gas. Heavy elements, what astronomers call metals, everything heavier than helium, are forged in stars in supernova. Finding metal-rich gas in a galaxy only a few 100 million years after the Big Bang means multiple generations of stars have already lived and died. That pushes the clock of galaxy evolution earlier, forcing us to rethink how fast the first structures assembled. Of course, extraordinary claims demand extraordinary caution. Early Webb papers sparked headlines about galaxies that break the universe. But many of those first candidates were based on photometric redshifts, estimates from colors alone. That method is powerful but can be fooled by dusty closer galaxies that mimic the colors of very distant ones. As spectroscopic follow-up has come in, some supposed record breakers have moved to more ordinary distances. Yet, even after this correction, a stubborn population of genuinely early, surprisingly bright galaxies remains. The tension is not a single dramatic outlier, but a statistical pattern. There seem to be more luminous galaxies at high redshift than standard models predicted. So what could be going on? One possibility is that our recipes for star formation in the early universe are wrong. Maybe the first stars formed more efficiently from pristine gas, or the initial mass function, the distribution of star masses at birth, was skewed toward massive, luminous stars. Another option is that feedback from supernovae and black holes was less effective at blowing gas out of small galaxies than we thought, allowing them to grow faster. Or perhaps the dark matter halos themselves assembled earlier or in a slightly different way than in our simulations. None of these ideas throw out LAL-CDM entirely, but they tweak the details of how baryons, normal matter, behave inside the dark matter scaffolding. And then there are more exotic suggestions, hovering at the edge of mainstream discussion. Some theorists have proposed dark stars, hypothetical early objects powered not by nuclear fusion, but by the annihilation of dark matter particles concentrated in dense halos. These would be puffy, cool, and extremely luminous in infrared, potentially masquerading as some of Webb's little red dots. Others explore modifications to dark energy or to gravity itself that could change the timeline of structure growth. Most cosmologists are cautious here. The bar for rewriting fundamental physics is high. But the fact that Webb has reopened these questions is itself profound. A telescope designed to study the first galaxies has instead turned them into a new kind of cosmic Rorschach test. Crucially, this is not a crisis of chaos, but of precision. The cosmic microwave background, baryon acoustic oscillations, and large-scale structure surveys still paint a remarkably consistent picture of a LAL-CDM universe. Webb is probing a different regime. Small scales, early times, messy astrophysics. It's like comparing a satellite photo of an entire continent to a street-level view of a single city block. If the city looks more built up than expected, you don't immediately doubt the existence of the continent, but you do start asking new questions about urban planning. In cosmology, those planning rules are the microphysics of gas, stars, and black holes. As more Webb data pour in, astronomers are refining their models, running new simulations, and, importantly, hunting for the most extreme outliers to test the limits of theory. Some little red dots will turn out to be ordinary galaxies seen in unusual ways. Others may host rapidly growing black holes, their light boosted by accretion. A few might be genuine monsters, forcing us to admit that the universe learned to build complexity faster than we imagined. And beyond the statistics and the jargon, there is a deeper shift. For the first time, we are not just inferring the early universe from relic radiation and equations, we are watching its first strange galaxies flicker into view. Because if these early galaxies already strain our models, the next question is even more unsettling. What happens when we stop looking at galaxies as a whole and start dissecting the mysterious engines blazing away inside their cores?